Hey there, science fans. Welcome to another exciting journey into the world of chemistry. Ever wondered what holds everything together? What makes the universe tick at the most fundamental level? From the water you drink to the air you breathe, it all comes down to chemical bonds. These invisible forces are the glue that holds the world together. These bonds are the forces that attract atoms to each other, forming molecules. Without them, life as we know it wouldn't exist. Think of them like tiny magnets, holding atoms together in a tight embrace. Just like magnets, these bonds can be incredibly strong or surprisingly weak. There are two main types of chemical bonds, ionic and covalent. Each type has its own unique characteristics and plays a crucial role in the chemistry of life. Ionic bonds form when one atom donates an electron to another atom. This transfer of electrons creates a bond that is both strong and stable. This creates ions, which are atoms with a positive or negative charge. Opposites attract, right? This attraction is the essence of ionic bonding. So, the positive and negative ions are drawn together like magnets, forming a strong bond. This bond is what gives ionic compounds their unique properties. Table salt, or NaCl, is a classic example of an ionic bond. The sodium and chlorine atoms come together to form a stable compound that we use every day. Covalent bonds, on the other hand, are all about sharing. Instead of transferring electrons, atoms in a covalent bond share them. In a covalent bond, atoms share electrons to achieve a stable electron configuration. This sharing creates a strong bond that holds the atoms together. It's like two kids sharing a toy to make each other happy. This mutual sharing is what makes covalent bonds so special. Water, or H2O, is a prime example of a molecule held together by covalent bonds. The hydrogen and oxygen atoms share electrons, creating a stable and essential molecule. These bonds are the foundation of chemistry. They determine the structure and properties of the molecules that make up everything around us. Understanding them unlocks the secrets of how molecules form, interact, and create the amazing diversity of matter we see around us. From the simplest molecules to the most complex structures, chemical bonds are at the heart of it all. So, buckle up, science fans. We're about to embark on a deeper exploration of these fascinating bonds. We're about to dive deeper into the fascinating world of chemical bonding. Get ready to uncover the mysteries that make our world so wonderfully complex and beautifully interconnected. Now, let's zoom in on covalent bonds and explore how they work at the atomic level. Covalent bonds are fascinating because they involve the sharing of electrons between atoms, creating a strong connection that holds molecules together. Valence bond theory, or VBT, comes to the rescue. This theory helps us understand the nature of these bonds by delving into the behavior of electrons and atomic orbitals. VBT explains covalent bonding by focusing on the overlap of atomic orbitals. When these orbitals overlap, they create a region where electrons can be shared between atoms, forming a bond. Think of atomic orbitals as the homes of electrons. Each orbital can hold a certain number of electrons, and these electrons occupy different energy levels within the atom. These orbitals have different shapes and energy levels. Some are spherical, while others are more complex, like dumbbells or cloverleafs. When atoms form covalent bonds, their atomic orbitals overlap, allowing electrons to be shared between them. This overlap creates a stable arrangement, lowering the energy of the system. It's like merging two houses into one, creating a shared space for the electrons. This shared space is what holds the atoms together in a molecule. But here's the catch. Sometimes atomic orbitals need a little makeover before they can overlap effectively. This is because the shapes and orientations of the orbitals might not be perfectly aligned for bonding. That's where hybridization comes in. Hybridization is a process that combines different atomic orbitals to form new, hybrid orbitals that are better suited for bonding. Hybridization is like renovating those atomic orbitals, combining them to create new, hybrid orbitals that are better suited for bonding. This process ensures that the orbitals can overlap more effectively. Imagine you're trying to fit two oddly shaped puzzle pieces together. At first, they might not fit perfectly because of their shapes. They might not fit perfectly at first. But with a little adjustment, you can reshape them to fit together snugly. But if you reshape them slightly, they can interlock snugly. This is similar to how hybridization works for atomic orbitals. That's what hybridization does for atomic orbitals. It allows them to overlap more effectively, forming stronger covalent bonds. It allows them to overlap more effectively, forming stronger covalent bonds. This results in a more stable and robust molecular structure, which is essential for the formation of complex molecules in chemistry. Have you ever noticed that molecules come in all sorts of shapes and sizes? From the simplest diatomic molecules to the most complex organic compounds, the diversity in molecular shapes is truly fascinating. Some are linear, some are bent, and others are even more complex. The variety in molecular geometry is not just random, it follows specific rules and principles. But why do molecules adopt these specific shapes? What governs the arrangement of atoms in a molecule? The answer lies in the valence shell electron pair repulsion, or VSEPR, theory. This theory is a cornerstone in understanding molecular geometry. VSEPR theory states that electron pairs around a central atom will repel each other. This repulsion is due to the negative charge of the electrons, which naturally push away from each other. They want to be as far apart as possible, just like students in a crowded classroom. Imagine students trying to find their own space in a packed room. They will spread out to minimize discomfort. This repulsion between electron pairs determines the three-dimensional shape of the molecule. The spatial arrangement of these electron pairs dictates how the atoms are positioned. Let's take water, or H2O, as an example. Water is a common molecule, yet its shape is quite unique and essential for its properties. Oxygen has two lone pairs of electrons and two bonding pairs, shared with the hydrogen atoms. These lone pairs are not involved in bonding, but still occupy space around the oxygen atom. These four electron pairs repel each other, pushing the hydrogen atoms closer together. The lone pairs exert a greater repulsive force than the bonding pairs, causing the molecule to bend. This results in a bent shape for the water molecule, like a boomerang. This bent shape is crucial for water's unique properties, such as its high boiling point and surface tension. Other molecules like carbon dioxide, or CO2, have a linear shape because the electron pairs are distributed symmetrically around the central carbon atom. In CO2, there are no lone pairs on the central carbon atom, allowing the molecule to remain linear. The VCPR theory helps us predict the shapes of countless molecules, providing valuable insights into their properties and behavior. Understanding molecular shapes is fundamental in fields like chemistry, biology, and materials science, influencing everything from drug design to the development of new materials. While VBT provides a useful framework for understanding covalent bonding, it has its limitations. That's where molecular orbital, or MO theory, steps in, offering a more comprehensive explanation of bonding. MO theory suggests that when atoms bond, their atomic orbitals combine to form molecular orbitals, which are spread out over the entire molecule. These molecular orbitals can be either bonding or anti-bonding. Bonding orbitals stabilize the molecule, while anti-bonding orbitals destabilize it. Think of it like mixing two colors of paint. If you mix blue and yellow, you get green, a new color that's different from the original two. Similarly, atomic orbitals combine to create molecular orbitals with unique properties. MO theory helps explain phenomena that VBT can't, such as the magnetic properties of molecules and the existence of molecules with unpaired electrons. It's a more complex theory, but it provides a deeper understanding of the nature of chemical bonding.